Hey everyone, welcome to Inside the Motion, where we explore the tech that keeps the mechanical world moving. I'm AJ, a mechanical engineering student.
And I'm Simon, also a mechanical engineering student, trying to make a sense of all this cool electronic stuff.
And hi everyone, I'm Jade, another ME student diving into the electronics world with curiosity and lots of questions.
Quick poll for our listeners. How many of you have actually opened up a phone or a gaming controller just to look at what's inside? Guilty? A charge over here.
Oh, you're guilty.
Same, just looking for sensor like hardware detective.
Oh yeah, right. Me too. But before we zoom in on accelerometers, let's talk a bit about sensors in general. A sensor is basically a device that detects something physical like temperature, motion, or pressure and turns that into data. And hey, if you're listening right now, pause and look around you. Your phone, your smartwatch, and at least one of them is sensing something about the environment.
Even your earbuds, accelerometers help detect taps and heel tilts for control. In mechanical system, we rely on all sorts of sensors like temperature sensors for engine control, pressure sensors in hydraulics, gyroscope in orientation, and of course accelerometer, our main focus for today.
Yeah.
So get ready to hear the word accelerometer about 2,200 times today.
How about we should start a counter?
That's fun.
Alright.
Now, not all the accelerometers are created equal. There are different types depending on how they measure acceleration. The most common are
First of all, we have capacitive accelerometers. These are widely used in smartphones. They detect changes in electrical capacitance as internal parts move. Second are piezoelectric accelerometers. They are often found in industrial equipment. They use materials that generate electric charge when stressed. Last are MEMS or micro electromechanical systems. These are tiny chip-sized sensors found in almost everything electronic today.
MEMS are especially important because they are small, cheap, and works really well with detecting motion in 3D spaces on the X, Y, and Z axis.
Today, we're focusing on one of the most widely used and fascinating sensors, the accelerometer. It's compact yet powerful, used in everything from your mobile phone to industrial robots and aerospace systems.
We'll go deep into how it works, where it's used, why it's especially relevant for us as mechanical engineering students, and what the future holds for this amazing lethal device. We've also lined up real-world examples and a case study to bring it all together.
That was smooth intro, Jade.
Thanks, bro. Been practicing that all my life.
Alright, let's accelerate into it. Pun intended.
Now, let us dive. What is an accelerometer?
So let's get into what accelerometer is. At its core, it's a sensor that measures acceleration, which is the rate of change of velocity over time.
In simpler terms, it tells us when something speeds up or slows down or changes in direction. It's different from a speedometer. While a speedometer tells you how fast you're going, an accelerometer tells you how fast you're changing speed.
Oh, it's the drama sensor.
The what now?
What?
Drama sensor, you know? It senses all the action, the
Okay.
sudden moves, big changes, drama. Yeah.
Okay.
For our ME friends, think of accelerations as a second derivative of displacement with respect to time. That's why it's so powerful. It tells us not just what happened, but how fascinating changing.
Yeah. It usually measures these in three axes: the X, Y, and the Z. This is why your phone screen knows how to rotate, or why fitness trackers know when you're walking or running.
Like what I mentioned earlier, the different type of accelerometers are capacitive, photosensitive, piezoelectric, and thermal. But the most common ones in consumer and engineering applications are MEMS, capacitive accelerometers.
Again, MEMS stands for Micro Electromechanical Systems. These are tiny mechanical structures fabricated on silicon chips. Inside, there's a tiny proof mass suspended by springs. When the device accelerates, the mass moves slightly and the sensor detects this movement as a change in capacitance.
Mechanical engineers, this is where your design intuition kicks in. stiffness, damping, resonance. Those spring mount concept from dynamics, these literally live inside MEMS chips. This capacitance change is converted into an electrical signal that can be interpreted by a microcontroller or computer.
What's cool is that the design balance sensitivity in size. If the structure is too stiff and it would move enough, if it's too loose, it might be too sensitive to noise. So mechanical engineers play a big role in tuning the design for the right application.
Random fact, the first mass-produced MEMS accelerometers were used in car airbags like this one I have.
Yeah.
They had to detect rapid deceleration in milliseconds to trigger the airbag deployment in a crash.
Wow, so that's high stakes stuff, right? No room for lag there.
Yeah, definitely not.
Definitely not a century one hitting snooze.
And nowadays, we carry them in our phones.
Eh, sana all.
Without even thinking it. It's pretty wild.
Pop quiz! If MAS sensors has too much damping, what happens? A. More sensitivity. B. Less motion detection. C. Higher power draw. Or D. It
I say
explodes.
It's D. Definitely D.
No, I say A.
Think it through. We'll answer it after this a bit.
A.
So the correct answer is B. Too much
Alright.
damping equals the prop mass resist movement equals to least responsiveness.
Wow. So now, let us move on to the mechanical engineering applications of accelerometers.
Ever heard that
What? Oh.
a noise from a compressor? That's the vibration data waiting to be captured.
Uh-oh.
Engineers use accelerometers to catch problems before the noise even starts.
Predictive maintenance is the unsung hero of engineering savings. Seriously, downtime can cost thousands per minute in some industry.
True.
That prompts us the question, as mechanical engineers, why do we care? Accelerometers are crucial tools in many of our fields.
For one, they use in vibration monitoring. Think about the rotating machinery in a manufacturing plant, motors, turbines, and compressors. If they start to vibrate more than usual, it could mean a misalignment or developing a fault.
Or worse, an expensive shutdown.
Yeah, no one must get that emergency call at 2 a.m.
True. Installing accelerometers on these machines let us track their health over time. This is called condition monitoring or predictive maintenance. It saves companies thousands of dollars by preventing unplanned breakdowns.
Okay.
Another big area is structural health monitoring. Engineers place accelerometers on bridges, buildings, and other large structures to detect movement during normal operation and during events like earthquake or strong winds.
In robotics, accelerometers help detect the tilt and orientation. This is important for balancing, especially in leg robots or drones.
So let's try an example.
Alright.
Tap on your desk. That's a forced input. Now imagine measuring how it wobbles with an accelerometer. That's modal analysis in action.
Modal analysis?
Yeah. Modal analysis is where we apply a force to a structure and measure how it vibrates. From that data, we get natural frequencies and mode shapes. That's essential for designing structures that don't resonate dissectingly.
Biomechanics is another field, at least where sensors that include accelerometer to measure motion, impact, technique, and physical therapies use them to monitor patient recovery and motion range.
Even inside vehicles, accelerometers are used for the dynamic suspension system, navigation, and stability control. Pretty much any system that moves can benefit from acceleration sensing.
Now, let's move on to best practices
Okay,
for
best practices.
accelerometers.
So let's
How-
go practical.
Yeah. So, how do we use these sensors effectively? It all starts with selecting the right sensor.
Try this. Imagine how you're designing a drone. What do you think you need? 2Gs or a 100Gs? Think about the type of movement it experiences.
If you said 2Gs, you're right. A drone isn't crash testing. It's fluttering, dipping, hovering. So small, fast changes equals lower range, higher sensitivity.
There are several factors to consider. First one is range. Are you measuring a subtle movement or big impacts? Common ranges are 2Gs, 10Gs, and up to 100Gs for crash testing. Excuse me. The other one is sensitivity. How finely do you want to detect movement? Next one is frequency response. High-speed vibration needs a sensor that responds quickly.
So mounting is also key. The sensor must be attached rigidly to the surface you want to monitor. If it's lost or poorly connected, it will pick up a false data or dampen the actual motion.
So no duct tape solutions, please.
Only if you want duct tape data.
Yeah. And also, wiring matters too. Use shielded cables to avoid electromagnetic interference and keep connections short and clean. For industrial setups, consider waterproof or ruggedized options.
Calibration is also a step people often skip. Each sensor has some bias or offset. Calibrate it regularly using known acceleration like gravity to ensure accuracy. Sensor placement is like real estate. Location, location, location. Bad mounting equals to bad data, and that is equals to bad decisions.
And we've all seen what happens when data looks right, but it isn't.
And don't forget data acquisition. Sampling rate matters. According to the sampling theory, you should sample at least twice the highest frequency component you're interested in. So if your machines vibrate at 500 Hz, samples it at 1 kHz or higher.
And also, filters can help clean your signal. A low-pass filter can remove high-frequency noise. High-pass filters can eliminate drift or gravity effects if you're only interested in dynamic acceleration.
Finally, process your data smartly. Use RMS values, FFTs, or even machine learning algorithms to detect patterns.
I have random pro tips.
Okay.
MAMS accelerometers are temperature sensitive. Keep that in mind that you're using them in an environment that heats up.
Oh, so don't leave them in next to your soldering iron.
Or in your car during summer in Manila.
Or here in CDO, right?
Yeah. Free hot.
Free hot water.
Now let's go to the future tech and trends. Looking to the future, accelerometers are getting more integrated, smarter, and energy efficient.
And we're seeing sensor fusion, where accelerometers are combined with gyroscope, magnetometers, and GPS to create inertial measurement units, or IMUs. These are used in self-driving cars, drones, and VR. And here's a challenge for our listener. Design a smart sensor for a skate park. What would you measure? Who uses data? Pause and bracelet and will wait.
Oh, okay, smart sensors are another trend. These sensors don't just collect data, they analyze it on board. Imagine an accelerometer that can send an alert only when something abnormal happens. That saves energy and bandwidth.
And then there's wireless sensors. They're used in hard-to-reach places like inside walls or moving parts to monitor equipment remotely.
Energy harvesting is big. Researchers are developing sensors that harvest energy from vibration themselves. That means you don't need batteries nor wires.
With the rise of the Internet of Things, accelerometers will be embedded in more devices from smart shoes to industrial equipment.
Yeah, and machine learning will also play a role. Imagine a sensor that learns the normal vibration of a machine and flags any deviation automatically. Think about it. What if the sensor not only said, "This motor is vibrating weirdly," but also learned your equipment's behavior and told you why?
Okay, so that's the leap from sensing to understanding.
Okay, I have a random fact. The ADXL 1005 from analog devices can measure up to 500 Gs with ultra-low noise.
Wow.
Ideal for high-speed industrial application, and that's cutting-edge stuff.
Yeah.
Alright. Time for a pop quiz. Just for fun and don't worry, no grades here.
Let's call it motion check. I'll ask and you answer, guys, alright?
Let's bring it on. I got my brains warmed up here.
Alright, for the question, what does accelerometer actually measure?
Acceleration. The rate of change of velocity, nailed it.
Yeah.
Correct, but I'll give you a bonus point if you said X, Y, and Z axis.
Yeah, you missed it, bro.
Yeah.
I don't
Too
love
bad.
that.
Okay, for the second question, what kind of accelerometer is typically used in a smartphone?
That would be a capacitive MEMS accelerometer. Super tiny, super clever.
10 out of 10, Jade.
I know, right?
Alright, for the third question, true or false? Accelerometers can detect orientation.
True, that's how your phone knows to rotate on the screen.
Right again, orientation is determined using gravity-based tilt sensing.
Alright, now it's my turn to throw one in. What does MEMS stand for?
Micro, electro, mechanical system.
Simon?
Yeah, micro electromechanical system. You ready for the acronym Olympics?
Okay.
Simon?
Nice job, team. If you got 3 or more or more right along with us, give yourself a high five. Just don't shake your phone too hard or your accelerometer might call it a win.
Yeah.
Let's jump back into application and see where all this sensing really comes to life. Imagine being Imagine being able to spot a faulty bearing before it becomes a problem.
That's what we call
Engineering foresight.
Oh my god!
Alright, so now let's move on to the case studies and example.
Let's look at some real-world examples. First, the analog devices ADXL50, one of the first capacitive MEMS accelerometers designed in collaboration with mechanical engineers in MIT. It measured up to 50 Gs and was used in car airbag systems.
Wow.
It integrated the mechanical sensors and electronic circuitry on one chip. A huge innovation at the time, it lowered costs and increased reliability.
This evolved into the ADXL 150 and ADXL 202, improving accuracy and
Okay.
reducing size. These are used in everything from sports gear to industrial machine. Let's break it down like a tech family tree. ADXL is like a grandparent, bulky but dependable, while ADXL 202 is the athletic grandkid, small, fast, and everywhere.
Another example is NASA Apollo lunar lander. They use accelerometer to measure descent rate and ensure smooth landing. That's a mission-critical engineering.
And there's other one also, the Millennium Bridge in London, experienced unexpected wobbling due to pedestrian walking resonance. Engineer installed accelerometer to study the problem and design a damping system.
Crash test dummies are packed with sensors. Accelerometers capture impact forces during vehicle crashes, helping design safer cars.
Okay, so turbine spin and critical condition, wind shears, temperature swings, and even lightning. Accelerometers track how blades flex under all that stress.
And the data they collect, used to schedule blade repairs before they break.
Oh.
In wind turbines, engineers place accelerometers on the blades and the hubs to detect imbalance, wear, or lightning strikes. It's part of the larger predictive maintenance system.
Even smartphones, engineers use accelerometer for screen rotation, shake detection, and even earthquake early warning system in some areas.
Yeah, these real-life uses shows just how important this small world sensor in the bigger world of mechanical systems. Now, for our listeners, next time you ride a train, feel the vibrations. If you were an engineer, where would you place an accelerometer?
I'll put it in the wheels.
I put it on the side mirror.
Okay, guys, let's wrap up. But before that, we've got time for a few listener questions. Ones you've actually opened from classmates or heard in labs.
Alright, from the first one, how does an accelerometer know the difference between motion and gravity? Alright.
So, good question from Ken Ladera. It said that accelerometer sense both, but using filters like high pass filter, you can isolate movement from the constant fall of gravity.
Here's another one that I've read. Can accelerometers be used underwater?
Totally, as long as the sensor is waterproof and rated for that
That's cool.
environment. They're used in underwater robotics, submersibles all the time.
There's another question right
So, last one, how do I know if I need a 2Gs or 100Gs accelerometer?
It depends on what you're measuring. Small motions, 2G is great. Crash testing or big impacts, you'll need a higher range like 100 Gs to avoid saturation.
Alright guys, we have a lot of great questions. Keep them coming. We might turn this into a regular segment.
We could even do a live Q&A episodes down the line.
Only if Simon does the theme song for it, right?
Ta 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 ta.
Oh no, bro! Stop that!
You got questions, we got motions.
Alright, okay, for now let's stick to sensors, alright?
Yeah, let's just stick to it. Now, guys, we've taken a deep dive into the world of accelerometers, from how they work to how we use them, best practices, future trends, and real case studies.
As a mechanical engineering student, learning about the sensor like this opens doors to so many applications, from machinery and to space mission.
Whether it's designing a safe car, a more efficient drone, or a smarter wearable, understanding acceleration is key.
So guys, thanks for hanging out with us on Inside the Motion. If you like this episode, give us a follow and stay tuned for more deep dives.
And of course, we would like to shout out our electronics instructor, Sir Chan, for the electronics department for making electronics fun.
Thanks for your patience, sir.
Thank you, sir.
No!
To our
I'm
listeners,
failing.
Keep,
Please
keep
don't
building,
fail us, sir.
keep learning, and stay curious. Alright,
1, 2, 3. Bye.
Catch up
you
next time.
Catch out!
Catch out.
Bro, i-check mo daw yung mabot. Tag-20 lang sa'yo.
20 lang.
No, 2025. Ay, yung video, Jade. Yung recording.
Oh, hindi na dito.